MTH-ALT space would be, but it's a bit bad in a sense. Let's see. If I take X to be a disk, just unit disk, and oh yes, thank you. And let me okay, this is Y. And X will be a quotient of this disk divided by equivalence relation, where the 2 points are equivalent if and only if they only lie on the boundary, and essentially their phase differs by a multiple of p, where for some generalized stuff with the disk, and then you do a quotient so that, say, for example, p equals 3, these triples of points, which are obtained by rotation by 2 pi divided by 3, they are all identified. This, and well, the question is what the fundamental group is this?
What? Keep that P. CP, Z over Z2. No?
Well, the X, this X.
No, I mean, you asked us the fundamental group.
Yeah, the fundamental group. Well, let's say 0. This is, I mean, it's connected space. This equivalent relation is this.
It looks like Z over B.
Yes. So this is too simple. You want something in between.
No, I mean, but the problem is using my count. How to do that using my count?
Well, you need to cover this. Well, in simplest cases, you just need to. I mean, it's enough to cover it like this by two. Well, the idea is to cover the space by something simple for which you can easily calculate from that. So here, let me take U. Let's say, so I want X to be union of 2 open sets such as, well, let me take U1 to be just, let's say subset is open disk with radius 1/2, and let's say U2, well, I can take, it doesn't matter precisely, it's, I can just take less than 1. And U2 take, I can put any number between 1 and 0, and because they are all homotopically equivalent. And this, and this is like this. Well, I mean, of course, I have to quotient over my equivalence relation. This is the open sets in the quotient, but of course, the quotient here does nothing, because the quotient only acts the points with unit unit length, unit absolute one, and then of course the pi 1 of Q1 is trivial because this is just a disk. This is normal factor this, which is homotopically equivalent to a point. You can just contract everything. And then pi1 of u2 is what is this? This is so I can sorry, this is it's not. Otherwise, it's not going to happen. Greater than 0. Right? Punctuate. U2 will be punctuate. So U2 is this, and U1 is this. So U2, so U1 I can deformation retract to a point, and U2 I can deformation retract to this to the circle. So this will be the same as pi2 of this boundary circle, which is this divided by quotient. But of course, if I for the circle, this quotient is just gives me again the circle. This is again there. So if I identify, I mean, just a statement is easy. If you want to be more explicit, is that divided as equivalence relation is homomorphic to another circle. This one. This is because I can just take the map, or the homomorphism can be realized by taking Z. P here. So what I want Z is sent to P here, and W send it to this. So this is well defined. So this doesn't depend on the choice of class here because I take the power here, and this is a well, this is the piece root is defined up to this place, so this is also well defined. Well, I have to class. Anyway, this is just a cover. This is just a cover. This map, the quotient, the quotient which I do here. Is just a covering map of circle from the circle. And the third ingredient is we want the intersection, the pi1 of the intersection, and the intersection is this annulus. So annulus is homotopically equivalent to a circle again, because you can deformation retracted annulus to any circle. Any circle centered at 0. So this is also Z. So now we have to calculate the one-compens theorem. Tells us that we need to calculate this. Quotient over, so I can see the quotient over, so I can define the maps G1, 2, this A1, B1, B2, A1, B1, and G2, 1, A1, B1, B2. These maps just induce the maps induced by the corresponding conclusions. And so So this group has a single generator. So let me. The three-group generated, say, by A. So it's just enough to calculate the image to determine the so these maps are just determined by the value of the generator. And so I just need to quotient here by the group, by the subgroup here in this free product generated by this combination of images of the generator in the intersection. So in general we have to do quotient over subgroup which is generated by all possible combinations like this, where A is any for all generators. All generators in Python. But see, here we have a single generator, so it's easy. And so we just need to determine how those maps act. So let's first G12. So this is let's determine G12. This is induced by embedding into U1. But U1 is trivial, so this is 0. So of course the generator here is just mapped up to 1. So what about this G21? So this is a map induced by embedding this annulus into this complement of a point here. This punctured disk quotient over equivalent relation. So of course the generator corresponds to just a single loop winding once around 0. But we need to express this generator in terms of the generator. Where does it mapped into the fundamental group of this P1 U2, and U2 was so U2 was obtained by taking first the deformation retract to the boundary and realizing that the boundary is another circle. But we see that if this deformation retract puts me this A cycle to this A cycle, if I push it to the boundary, it becomes a cycle like this. And we see that this cycle now, well, in this particular case, it's P equals 8, it winds, so it winds once around this, around the circle here, but once we do a quotient, it will wind 3 times over the circle which obtained in the quotient here. Because this the quotient map in this particular case. The projection. So this A here. Well, if it's let's say this is generated by some B, A will go to the B cube. This is trivial, and this is generated by B, so we get a group. We can forget about this, so we get a quotient of a free group generated by B. Well, in general, this is not C, this is P. And this is a cyclic group of order P. or if you want, I mean, this is a this is more or less the most simple non-trivial example. Come on. Did you have some questions? Still have some questions? Please ask.
How to come up from the definition in the homework to this space? I mean,
no, this is not in home. This is not in homework. No? This is simple. You want this is a simple example. I'm saying this is a kind of analogous, but in the homework, there is easy. I mean, there is one can also use a similar trick. So this was defined like this, defined by this quotient, and you can also consider this. Covered by two open sets. One of them will be defined by subsets. Subset is this condition that, let's see, well, z1 is greater than 0. Absolutely. And the other, I mean, of course, I can see that this is subset here. And the other is and then you can show that each of them is homomorphic to a disk times this one, for which you know the phenomenon. It's just and you can also show that the intersection is it's torus. It will be of the form torus times an interval, but it's well up to it's homotopy. It's the intersection deformation retracts to a torus. So it's torus times an interval, but you can always retract it. So you have. So phi 1 of the intersection will be z squared. So it has some two generators, say A and B. Essentially, what you want to in this length space, you end up calculating a certain quotient. This one. But how exactly this Z2 subgroup is embedded here, you have to determine. It's determined by this inclusion maps, which requires some work. The result will also be ZP. But you have to, I mean, the inclusions, or how your torus is included into these UIs. Determines how this Z2 is embedded in Z times Z star Z. I mean, I'm not, the details, I mean, you will see either in tutorials, but there will be written solution. But again, this problem is intended to be hard. Not, but I mean, the level, for example, will be lower than the hardest problems of the homework, so it shouldn't worry too much. Any other questions about one company using one company's theory? So yeah, we want to finish some theorems about covering spaces, and then we will start a new topic, a new big topic, homology. Okay, so last time we proved existence of a universal cover for the topological space X, which satisfies certain technical assumptions. And so this was the universal cover was a covering space with a trivial fundamental group. Now we want to generalize this result to the case of a universal of finding covering space such that with a given fundamental group, not necessarily trivial. So we will, okay, so what that's saying, we'll have the same assumptions. So X will be path connected, locally, path connected, semi-locally, simply connected. So let me take.
Locally path connected?
Yes, locally path connected.
Isn't a path connected space locally path connected?
No, the path connected doesn't for neither of them imply other. Then this, okay, so for any subgroup H, well, we should come to all lectures. You should come to all lectures and finish. So for any subgroup there exists a covering topological space XH such that the image of its fundamental group is this subgroup. Of course, we are talking about we need to fix some base point. x0 tilde. Because we know that P star is injective, so this H, the pi1 itself of XH is homomorphic, sorry, isomorphic to H. So the last lecture we improved this. H equals 1. So let X. So let me start. So we already know that we can construct X tilde, the covering space with H being 1. So let me take it. So let X tilde be the universal cover of X as constructed before. So a reminder, we construct it as maybe it's useful to remind you. So X, we started X, and there was so we considered some point. So X tilde was defined by. So considering lifting, defining the preimage of the would be carrying out, such as the preimage of if I take some point here, and to determine what is preimage, its preimage is given by path homotopy classes of all possible paths which start as a fixed base point in X. Take some pass F and G, they give me generically they give me two different, which go to the same point here. This will give me generically two different images. Like this one here. So this is just a reminder. And let me define the following equivalence relation on points in X tilde. So again, the points in X tilde, universal cover was just path homotopy classes of paths in X, our original space. So for homotopy classes of two paths, F and say F tilde, they declare to be equivalent. First, if they have the same endpoints, so in particular this means they are both in the preimage of the same point in X, and if you consider the following, the class of the following composition, so I start with F, and then I compose it with F prime bar. So this will be a loop. This will be a loop in X. So essentially, let me instead of G here put F prime. So this composition will be a loop in X. So this will be, I want to require to be an element in my subgroup H. Okay, and then what I want to define is I want to define my space XH as a portion of X with respect to this equivalence equation. So X tilde. So this kind of explains the meaning of the universal cover. So this is universal in the sense any other covering space I can realize by quotient my universal cover. And so last time we worked hard to kind of endow this X tilde with topology and so on, but here it's easier. So it's just topology will be the standard topology given by this quotient. Okay, but we still need to argue a little that this will be a covering space. This is a required fundamental group. So we know that. So let me define covering map as follows. So I take a so the points in X tilde were classes of paths in X. But then I'm going to first consider I want to consider equivalence classes of this equivalence classes with respect to this new equivalence relation. So we double. That's why there are double brackets. So the exterior bracket means this equivalence, additional equivalence relation. And this I map as in the universal cover case. I just map it to the value at the endpoint. Okay. And we want to check this is a covering map. Check this, and so we know that. So first, let me know that if 2 points in XH in X tilde are equivalent, this class is equivalent. This is equivalent to the condition. This happens if and only if these guys are also equivalent. Because this combined with some H, some other paths doesn't modify, doesn't change this additional condition. And of course, the endpoints still will be consistent. Okay. So this means that so reminder that last time we constructed so to define a base in the topology of X tilde, we constructed these guys labeled by U being an open set in X and F being a path in X. So this is defined, I remind you, this was defined in previous lecture as follows. So this was, this is define me a subset, define an open subset X tilde. And classes of maps constructed by the following composition, where the endpoint, such that endpoint of H belongs to U. And U, of course, it was assumed to be path connected and such that its image of this fundamental group inside X is trivial. So this is just from the last lecture. Okay, so and so it follows from this observation follows that so if if F is equivalent to F prime, this means all points the corresponding open sets are fireworks identified. Identified under this equivalence relation. That means particular the P inverse of U will be. So what happened for universal power? P inverse of U was this union of the following open sets in X tilde, so we argued that indeed they are all disjoint and they are all homomorphic to itself. So for because of this observation, for when you consider this quotient, this is so if you consider quotient of this would be the same as just taking the union of U F with fixed class of F, because well, here it was a disjoint union of sets homomorphic to each other, and what the quotient does, it's just it was a union like this. What quotient does is just we identify some of them. We identify into these classes, and this still will be a union of this form. And indeed, so we see that P satisfies the properties of the covering of the covering. Finally, so we want to check that indeed the fundamental, the image of P star will be H. So let's see. So if so by definition, what is the image of P star? So this is elements in the fundamental group of X, such that they lift to loops in XH. F tilde is a unique lift of a pass in X to pass in XH, such that it starts with a fixed base point X0 tilde. So the non-trivial condition here is that the lift is such that F, the endpoint, is also X0 tilde. So we need to fix a base point in XH, and the way to do this is just define it as a double equivalence class of a constant pass in X. So the universal power, we just consider it without external brackets. Like this, now we take the first equation. That's why the second brackets. And okay. So we need to understand what this condition means, that the endpoint of the lifted path is the same as this X tilde, X0 tilde. Okay, so as a similarly to what happened last time, so we can start the lift just by the following construction, that f tilde of s is a class of a certain parse fs, where fs of t f of s times t. There's a path which goes kind of truncated version of the path f, and so this provides the lift, and then this condition just means that so of course we know that f of 1 is the same as f. So this condition means that the class of f itself is the same as class of the constant. And what this means, so by definition of this equivalence relation which we introduced, this means that the class of f is equivalent to the class of Cx0, where this was an equivalence relation which we introduced. And but this equivalence relation meant two things. First of all, the endpoints of these two guys should be the same, and the second condition was that their composition should be in my subgroup H. And this just means that the f itself, since this represents a trivial element in the fundamental group, this means just the f itself is inside my subgroup H of phi1 x and 0. Okay, so this indeed, so we show that any element in the image is indeed an element here at H. And so this is actually, this can go, so this is everywhere it was if and only if. Right? So we can go over, this means that indeed the image of P star is the same as H. Proof of the proposition about existence of a covering space with a given which corresponds to a given subgroup. Questions? I mean, it's hard to give an example. So this is a very simple example. So let me take x to be S1. So again, as before, let me realize S1 as R mod Z. And so there was a, we constructed so before there was so the universal cover X tilde we realized by R here. So clearly the fundamental group is indetrivial and the covering is just realized by taking some T here and considering it's T mod 1, right? The covering mod just corresponds to this quotient. And there also was, so what about, let me take the subgroup. So what are the subgroups of Z's? So all subgroup of Z's, they are of this form. They are multiples of n, some integer number. And you can see there the covering space corresponding to this subgroup H, which is just described by some integer number, can be realized by quotient X tilde by well, let me see it this way. So I can realize. So we know. So from one point of, so there. I mean, we can just present example of the covering space corresponding to the subgroup, and it's easy to see that one can provide such example by taking XH to be just S1, and the corresponding covering map, so it should be map from S1 to S1, just realized by taking, so here if I take, if I have some number T mod 1, I take it to N T mod 1. This is what we already discussed. At some point with S1, and the other S1 covers n times this one. And more explicitly, the covering map is given to this. But we can also realize this X to the H as a quotient of the universal cover by the group, by a certain action of this group H, which is R divided by N Z. And this is, of course, the other way to get this, circle.
And in this case, what is the projection?
So the projection is this, and well, the projection is just if I write it like this, I have to write. And so this is well, if I write it like this, so I have some number t mod m, and I map it just to t. So this is equivalent just by scaling t. This is equivalent. This is equivalent to this. It's the same as well. Maybe it's better to introduce some variable. Yes. So I can scale. I can say that my s is m times t. So we have n times t mod m. This is the same as this class defines t mod 1. Other questions?
With this proposition, can we prove that any group is a fundamental group of something? Or do we need something more?
Well, in this, no, we need something more, because here we show that any here we show that any, if you have something, we can analyze any subgroup of it also as fundamental groups. It's not enough. But in principle, yeah, in principle, it's possible to show that any group, for any group one can construct a topological space such that its fundamental group is this given group. If you're interested, we're not going to have time to talk about this. This is called Algebraic spaces. An Algebraic, so if you want to search, interesting, an Algebraic space, which is denoted by TG1, is such as a space equal to G, but there are also additional conditions that what is called high homotopy groups are working with one. Some additional, you can require some additional. And that exists, it can be constructed for any, it can be constructed.
What is this called?
Algebraic space. But we also want to show that we also want to show some sort of uniqueness, in a sense that there is, in a certain sense, there is a unique for a given. So we show the existence of a covering space with prescribed for a prescribed subgroup. So we want to show some. We want to argue some uniqueness. But of course, uniqueness will be only up to some isomorphism. So we have to define what we need. First, we want to define what do we mean by a kind of when do we want to say that two covering spaces are the same? In what sense they're the same? And isomorphism. So we want to define the notion of isomorphism between covering spaces. say normal difference between cover space x1 tilde and x2 tilde. So of a given fixed topological space X is a homeomorphism. So phi seems that the following diagram is commutative. So of course necessarily we want to show that, well, they're the same kind of as topological spaces, they're homomorphic, but moreover we want this homomorphism to preserve this covering map structure. So we want this, of course it's, since it's a homomorphism it has inverse, so we can also go this way around. So we want this these projections to commute with this homomorphism. So of course it's more or less obvious that this defines an equivalence relation. Equivalence relation of the, so we fix some topological space X and we consider all possible topological spaces which cover this space. And this is equivalence relation on this collection of these topological spaces that cover. Okay, and so the next proposition is about uniqueness of the correspondence of uniqueness of a covering space with a prescribed, essentially prescribed fundamental, namely the following. So here we assume, to show uniqueness we can use a bit slightly weaker assumptions. So X will be plus connected and locally plus connected. So being semi-locally simply connected is actually necessary condition for space. Well, okay, sorry. Yeah, we don't require here semi-local. We don't need to require here semi-locally simplified. So then, a pair of covers. Index I will be 1 or 2. We consider a pair of covering spaces xi tilde. And so I fix a base point in each of them. So this is mapped to a fixed base point x0, x0. And the same as the isomorphic for some phi. So phi will be a homomorphism between between x1 tilde and x2 tilde. Such that, so we require, so the statement, the homomorphism here is such that it relates this fixed base point between each other. X1 tilde is mapped to x2 tilde. So the existence of phi, which satisfies this of this isomorphism, which kind of preserves a this is what is called base point preserving isomorphism. Base point. So existence of such isomorphism is equivalent, it shows it's equivalent to the statement that the images of the corresponding push forwards are the same. Was it's equality between subgroups in X. But I will say that for a fixed subgroup there is unique cover corresponding to this subgroup. Okay. How do we show this? First, let us show it this way. So suppose there is isomorphism, this covers are isomorphic, then these corresponding subgroups are the same. So by definition of the isomorphism, we have the following relation between these covering maps and phi. In particular, P1 equals P2 times phi, and this, of course, implies that if you consider this, take the push forward of both sides, this in particular implies that image of phi1 star is inside the image of P2 star, right? And if I take, but we also have a relation this way, right? Phi inverse. And this implies the image P2 star is inside the image P1 star. Of course, combining both, we say we learn that it's the same. Okay, so what about the other? So previously we showed that if we the lifting the criteria to lift certain functions. So if you have a function from some space to another space, and you can always lift it to the universal cover of this second space, and this lift is unique if we fix a base point. Because we show if the lifts they coincide at one point, then they coincide everywhere. By lifting criterion, this is one of the propositions that we had before, there exists a lift P1 tilde will be a map from x1 tilde x to x2 tilde which lifts P1, which was a map from x1 tilde to x. So this was the lift in the following diagram. So we had so there was a map from x1 tilde to x, which is P1, and then you consider, and in this case we consider x2 tilde to be a covering space. So the covering map here is P2. And we wanted the statement that P1 tilde is the lift in this diagram. And in particular, this means that P2 satisfies the condition that P2, this composition is P1. So we found a function P1 tilde which satisfies this. And similarly, there exists lift P2 tilde in this diagram. So I can see the map from x2 tilde. So I just swap 1 and 2 here. x1 tilde P1 P1 here P2, and this will be our lift P2 tilde. So we lift P2 here with respect to P1. And here we lift it P1 with respect to P2. Okay, and this means that, so in terms of the composition, it just means that P1, P2 tilde equals P2, right? So let me note it by this. So now I want to use this too. Two relations. So let me do the following. Let me multiply. So let me take, for example, this, and I multiply it, and I compose it from the right with P1 tilde. So I get. So let me say this is what is this? Let's say A. B. So first I use this very, I take this and I compose it with P1 tilde here. But if I compose it with P1 tilde here, I can use this B form. So this will be just P1. So I get this P1. And okay. So now let me note. So how can I interpret this this condition? So I can interpret this condition as so if I put now brackets like this, I can interpret it as the following. This relation is the following commutative diagram. This might be a bit confusing, but just if you write it in terms of the diagram, this will be clear. That's why these diagrams actually will be more intuitive than this the formulas like this. So if I write it in the diagram, I write it like this. Okay, so P1, P1 in both cases they are maps from x1 tilde to x. And this means, so the equality comprises that this guy here is the lift of P1 with respect to P1 itself. Alright? This realizes this. But of course, we also have another lift. If you have, if you want to lift P1 with respect to P1, you can also lift it by just acting by identity. Right? This is, of course, will be a lift. So we also know that since all those this was so we know that this composition, if I act it on my base point here, x1 tilde, it gives me x1 tilde itself, right? Because of the here we used the fact, I mean, we used, this was the lifts were such that the P1 tilde, so it's here this the base point was x0 tilde, and its preimage was x1 tilde, and so here the preimage was x2 tilde in particular, and x1 tilde. So we require P1 tilde to be a unique lift such that it brings x1 tilde to x2 tilde. And the other way around for P2T. So we have this condition, and of course also if I act by identity on x1 tilde, this is also x1 tilde. And therefore we know that if two lifts coincide at some point, they coincide everywhere. This means this should be the same as this. Particular P2, this means that this combination, this composition is just identity on x1 tilde by uniqueness of a lift. Of a lift such that, so we use that this uniqueness is a coincide at one point. Two lifts are the same, they coincide. And similarly, we have P1 tilde, P2 tilde. Just repeating the same argument, but we swap at 1 and 2. This is the identity on x2 tilde. And so we have two continuous maps between spaces x1 tilde and x2 tilde, so this is the inverse to each other. This means that P1 tilde is a P1 tilde provides another one. There's a homomorphism between x1 and x2 tilde, homomorphism because of this, because it's left and right inverse, and of course it commutes by this construction, it commutes this projection. So it's indeed as far as the isomorphism between the covering spaces. Questions? So yeah, we're almost okay. Let me. So essentially, what we can combine the statements which we have already proved to formulate this following theorem, which can be. So the statement can be sometimes called Galois correspondence. That means therefore there is a projection, one-to-one correspondence between base point zeroing isomorphism classes of covering spaces X, algebraic space X, and subgroups of Y1. The correspondence is realized so before for a covering space X with subgroup corresponding subgroup is P star. Okay, the base point preserving means that the homomorphisms which enters in the definition of the isomorphism not just preserves, not just commutes with these covering maps, but it also maps the lift of the takes the lift of the base point of one space to the lift of the base point. Okay. But one can kind of if you don't assume so for arbitrary isomorphisms, not base point have to consider conjugacy process. So this is, I mean, roughly it just follows from the fact that if you change base point, this we know that change of base points act by a conjugation action. X. So yeah, of course I need to. We need to impose this assumption. This is path connected. So X is a topological space which is path connected, locally path connected. And semi-locally. Simply. So in particular, for this example with the circle, so for any subgroup, we constructed the covering space. So now we know that there is not this, the examples which you gave. This is the only example to isomorphism. No other. So for Islam, we construct all possible covering spaces. Any questions? So the next lecture is start. Sorry, no, it's not time, but the next lecture we start homology. Well, maybe make an announcement. Homology. So one feature. So for fundamental group, so we learned that there is a fundamental group can mess with the following. In a sense, a map, roughly speaking, but it's actually a function. So kind of for each topological space, we actually be precise one because it's based, sorry, pointed topological spaces. So we fix, we want to fix some point. Model and by one gives me a group. And moreover, I can quotient over homotopy equivalence. And here I can quotient over isomorphism. And for homology, so the input will be also a topological space. Actually, not necessarily. We cannot do without point. Well, there's a version of pointed, but there's also a version without point. It's a topological space, and to it we associate a kind of a collection of abelian group, but we also formulate a z-graded abelian groups. And here, of course, is up to isomorphism. This only depends on the homotopy equivalence. So in certain sense, since we know that there are always abelian groups here, by construction this is just abelian groups. So in a sense this is easier.